Hello everyone, today we will continue learning the secrets of logistic regression as we delve deeper into understanding all the necessary information required to build logistic regression from scratch. First, we generate synthetic data using make classification function. This data consists of a single feature and 25 samples with one informative feature per class. We'll then pre-process the data using standardization to ensure our features have a mean of 0 and a standard deviation of 1. Then, we train the model on the pre-processed data using the fit method, where X represents the features and Y represents the target labels. Let's model the optimization process ourselves. We'll draw a 3D loss function since we have two weights that the loss varies with. There are two perspectives ours and scikit-learn's realization. We can calculate gradients at any point of this function and move along the gradient's direction until we reach the minimum point. Let's use our dataset for simplicity. We notice that we only have features. Therefore, we need to write separate expressions for the bias weight to calculate its gradient and optimize it. To address this, create a constant feature that is equal to 1 everywhere. This will give us an array of units that we will concatenate with the original dataset. Now we will implement the special function where we calculate the logarithmic loss. The function takes the true target value and the predicted probability as input. We handle cases where the predicted probability is 0 or 1 by adding a small value. If the predicted probability is 0 for an object of the first class, for example, the model predicts with 100% certainty that a yellow object is purple, resulting in a probability of 0 for the yellow class. We add a tiny value to ensure the logarithm doesn't result in an error. Similarly, if the predicted probability is 1 for an object of the 0 class, we subtract a tiny value from 1 to avoid the logarithm of 0. We calculate the loss for each class, add them together, and divide by the number of objects to get the average loss per object. Here, by the way, we can make sure that we could have errors if we would not add with you a tiny value. Let's remove it for the first class, that is, when the model will be predicts for our first class that it is 100% 0, that it is the first real one, but the model thinks it is 0. That is, it has 0 probability of being a yellow class. It will drop a not-so-pretty value that is equal to infinity. And there is an error that we have a 0 logarithm. So we have correctly protected ourselves by adding a small little value so that there are no zeros in the logarithm. Let's train logistic regression using gradient descent. We'll start by initializing the weights. We have two attributes, one constant attribute for the bias weight and another attribute for which we need to train a specific weight. We'll also set the learning rate. We'll train for 250 iterations in a loop. In each iteration, we'll calculate the gradient using the previously defined function. We'll multiply the gradient by the learning rate and subtract it from the current weights to update them. This process helps us move towards minimal errors and obtain new weights. We'll also check for the stopping criteria. If the difference between the current weights and the previous weights is small, indicating that the weights are not changing significantly, we'll stop training. We'll calculate this difference using the Euclidean distance between the weights at each iteration and check if it's less than a predefined epsilon value. Additionally, every 8th iteration, we'll calculate the predicted probabilities and compare them with a cutoff value of 0.5. If the predicted probability is greater than 0.5, we'll classify it as belonging to the positive class. Let's display the loss function and metric on the screen and visualize the predictions of a linear regression model by multiplying the weights by the features and displaying them. Initially, at iteration 0, the line that separates the classes is incorrect, indicating poor predictions. As we progress to iteration 80, the line starts aligning in the correct direction, though the predictions are still inaccurate. By iteration 160, the line begins to bend, suggesting better predictions. Finally, at iteration 240, the line represents the best separation between the classes and the model's predictions are accurate. This improvement is reflected in the decreasing loss function and increasing metric, which indicate that the model is learning and improving over time. Now perform logistic regression for two features, making it multi-dimensional. We'll generate our own data with 2 useful features and 0 useless ones. We'll ensure to fix the randomness. We'll visualize these points together. We have a class of purple and a class of yellow. Let's take a scalar logistic regression with you. We train it, take the coefficient, take the bias term, make a prediction on this model, and get a class label 0 for the first object. We can also make another prediction using the coefficients applied to the features, Summing them up and adding the bias term, we get minus 0.74. This is what came out of linear regression. Let's put together a table with the actual target values of our objects, the features of our objects, the predicted class label from the scikit-learn version, and the predicted probability. We calculated the probability ourselves without using any model by taking the scalar product of the features and adding the bias term. Then we can check if the probability is greater than 0.5. If it is, it's the first class. If not, it's the zero class. Now let's see how accurate the model was. We manually calculated it and also used the score method. Our metric is 0.92. Let's visualize how well our model made predictions and how correct the line was. We'll take points on a grid and make predictions for each of these grid points. We'll generate many points with a small step from the minimum to the maximum x and y values. Then we'll form a grid of these values to make predictions at each point. We pass these points to our model, make predictions, and use a peak mesh to visualize them. If the probability is above 0.5, it will be blue, representing the predicted classes. It turns out quite well. We only make errors in 1, 2, 3, or 4 points. We've almost achieved perfection. This is the scikit-learn implementation of logistic regression. Let's create our logistic regression model. Remember that to make our model easier to train, we can add a constant feature that is always equal to 1. By doing this, we can add our bias weight to this constant feature. We will use the familiar functions for calculating the loss and its gradient. Also, we can create a function for visualization. In this visualization function, we will pass the weights in the grid of features we formed earlier. To this grid of features, we add a constant feature of value 1. By matrix multiplication with the weights, we get predicted probabilities. If the predicted probability is greater than or equal to 0.5, it will be the first class. If not, it will be the zero class. Now, let's train our logistic regression model manually, which we will do below. This is a preparation for visualization. We'll create a plot where each class is represented by a different color. For training, we start by initializing the weights. We have 3 features, 1 for the bias weight and 2 actual features. We also set the learning rate and check if the weights are not changing too much. We'll train for 250 iterations, updating the weights based on the gradient, which is the direction opposite to the gradient with a slightly reduced learning rate. If the new weights are very similar to the previous ones, we exit the training loop. Every 70th operation, we output the predicted probabilities and compare them with 0.5. If greater, it's the first class. If not, it's the zero class. We calculate and visualize our separating line. Let's see what happens. In the initial operation, the line was large and went in the wrong direction. According to the model, the red class is here, and the purple class is there, which is the opposite. Therefore, the accuracy is low, and the error is high. But the model is starting to get better. The metric is already 2 because the slope of the line changed from the top with red points to the bottom with purple points becoming much smaller. In the 140th operation, the loss is even smaller, and the line takes on a more familiar, correct slope. We continue. The slope becomes even more familiar. However, there is an additional point here that we missed, but in the end, the implementation of our model is quite good. We only make mistakes in 1, 2, 3, or 4 points. We found the best weights for this model manually through gradient descent. This is how our session slowly ends. In this session, we looked at logistic regression, transitioning smoothly from linear regression to logistic regression. We looked at how the loss function is derived from scratch, training logistic regression for a one-dimensional situation when there is only one feature, and for a two-dimensional technical, multi-dimensional situation when there are 2 features. This is easy to visualize, as we can perceive it visually. We also trained logistic regression using scikit-learn and visually interpreted what logistic regression is through visualization. That's all for us. Thank you for your attention. Wishing you good luck in your studies and goodbye for now.